Hello everyone and welcome to our lesson on 12.7 conditional probability. And conditional probability is used to solve problems involving dependent events. Now here's just a little video introing what we mean by conditional probability with a couple real-life examples for you.
I'm Philip Brokum, and this is an introduction to conditional probability. We're going to start with an example involving O.J. Simpson. During his trial, his defense lawyer used a statistic similar to the following. 99% of the time, men who beat their wives don't end up killing them. Therefore, even if O.J. Simpson beat his wife, it's almost certain that he didn't kill her. Now, even if that statistic is true, the conclusion is false, because an important statistic was left out. Here is a slightly less misleading statement. 99% of the time, men who beat their wives don't end up killing them. However, of the wives who are beaten and later killed, 90% of them are killed by their husbands. Do you see the difference? Of course, most people don't kill their wives. But in the small percent of cases where the wife is killed, it's almost always the husband who did it. Let's try another one. In this example, I'm going to use drunk drivers. 99% of the time, you won't get into an accident when you drive drunk. Therefore, driving drunk is safe. False. Again, here's a slightly less misleading statement. 99% of the time, you won't get into an accident when you drive drunk. However, 90% of all auto accidents involve alcohol. Do you see the difference now? Conditional probability is all about narrowing down the set of possible circumstances so that the statistics can be measured more accurately. Sure, 99% of the time, beaten wives aren't killed, but O.J. Simpson's wife was killed. We are no longer talking about the 99% of cases where the wife lives because she didn't live. We are already in the unlikely 1% case where the wife is killed. Any statistics relating to the other 99% of cases don't apply anymore. This is conditional probability, with the condition being that the wife was in fact killed. In my next example, I'm going to focus on coin tossing. Here's the coin I toss with my left hand. Here's the coin I toss with my right hand. So I'm tossing two coins. And here are the possible outcomes. The left-hand coin could be heads up, and the right-hand coin could also be heads up. Or the left-hand coin could be heads up, and the right-hand coin could be tails up. Or I could get tails and heads, or two tails. There are four possible outcomes. Here is the question. What is the probability that I get two heads? If you've done probability before, this is going to be really easy. There are four ways I could flip two coins, and in one of those ways I get two heads. Therefore, the probability is 1 out of 4, or 1/4. Let's try a hard one. Given that one coin is heads, what is the probability that the other coin is also heads? It is not 1/2. You have to be careful here. The condition that one coin is heads rules out the possibility of getting two tails. Of the remaining three ways the coins could be flipped, only one results in both coins being heads. Therefore, the probability is 1/3. It makes sense if you think about it. The probability of getting two heads is 1/4. If you know that you already have one head, surely the probability must go up a little bit, right? You are already halfway there, after all. In this case, it increases to 1/3. Let me see if I can really confuse you. Given that the left-hand coin is heads up, what's the probability that the other coin is also heads up? Be careful, this is not the same question. In this case, two of the four possible outcomes are eliminated. Of the two remaining possible outcomes, one of them results in both coins being heads for a probability of 1/2. Let me do a quick summary. Starting from a blank slate with no extra information, the probability of getting 2 heads is 1/4. If we have more information, if we can guarantee the condition that at least one coin is heads, that increases our odds to 1/3. With even more information, the knowledge of which coin is heads, we increase our odds up to 1/2. Using conditions to narrow down the number of possible outcomes, we can get more accurate statistics for a given circumstance. I'm going to end the slides here and just say a few words about probability. It's hard, and conditional probability is really hard. Here's my advice if you're just getting into it. Don't think about it. I know you thought you'd never hear me say that, but trust me, if you try to think about it, you're gonna get it wrong. Probability is very counterintuitive. When you're just starting out, the only surefire way to get it right is to list out all the possibilities and count them. Or if you can't count them, write out the numbers and add them up. It's the only way to make sure, and the only way to keep yourself from getting confused. Anyway, probability is my favorite field of math. I love it. I think it's awesome, precisely because it's so hard to understand. So I wish you luck. I hope you enjoyed the video, and I hope you now have a at least decent understanding of what conditional probability is.
So let's talk a little bit more about dependent events. So dependent events are going to happen when experiments are done with multiple events without replacement. Okay, so by not replacing an item, the second choice that you make is dependent on what happened in that first event. Now the probability of the second event is affected by whether the first event happens or not. So this would also be a dependent event. And dependence can also be set up the way a question is worded. So for example, if I'm going to draw 2 cards and I look at what I got for the first card, I can figure out my chances of getting a second card. Okay, it gives me some information and it helps narrow down my choices. Or if I'm trying to guess a card that you drew, my chances of guessing correctly would increase if you told me that the card was a face card. It's the same concept with card counting. So this brings us to our conditional probability formula. It says for any 2 events, event 1 and event 2, the probability of event 2 happening, given that event 1 has already happened, is the number of sample points in common to event 1 and event 2 divided by the number of sample points in event 1. Okay, so when we look at this, this is almost like our division sign right here. Okay, we think about it the same way. And event 1 becomes our number that goes on the bottom. Okay, and this becomes the pool that we're now drawing from. And what we have to say is out of that event 1, how many event 2s are there? Okay, and so the in common number happens on the top. So let's use this to find the following probabilities. Example 1 says a single card is selected from a deck of cards. Find the probability that it is a club given that it is black. Okay, so what we're looking for here is the probability of getting a club given the card is black. Okay, now looking at this, we would call this event 1 and this would be event 2. What we do is we assume that this has happened. So we need to say, well, how many black cards are there? Well, there's 26 black cards. And then we say, well, out of these 26, how many of them are clubs? So we just say, how many black cards are also clubs? Okay, and the answer there would be 13. And so this kind of sets up our division problem for us. Okay, so another way we can think about it is if we take the number of black clubs and divide it by the number of black cards. Okay, so the number of blacks is going to go on the bottom. That's 26. And then out of those blacks, 13 are clubs, so we have 13 on top. And here we get 1/2, or 50%. All right, let's move on. In our next example, we have a two-child family, and we want to find the probability of having two girls if you know at least one is a girl, and two girls given the older child is a girl. So in our first example here, we don't really have any information. We just need to see what's the probability of finding two girls. In letter B, we get a little more information. Here we know at least one is a girl. And then in letter C, we know even more specific information that the older child is a girl. To do these problems successfully, you need to find the sample space. And for this, we're going to use a tree diagram. And it's important. Order of events might matter depending on the question, especially in conditional probability. So we need to make sure we keep these events in order. So to do this problem, let's make a sample space. Okay, so for our first child, it can be a boy or it can be a girl. And then for the second child, it can also be a boy or a girl. So this is going to branch off, boy, girl. And then from a girl, it can still branch off to a boy and a girl. So we'll follow each of these branches, and we'll get our sample space of boy, 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 girl, girl, boy, and girl, girl. So looking at this first one, we're looking for the probability of two girls. Okay, so that's all we have to go with. So looking out of all these sample points, there is one that has two girls. So we have 1 out of 4, or 25%. So this is really not a conditional probability problem. In letter B, it says two girls if you know at least one is a girl. Now in this case, this is a condition. So we're looking for the probability of the family having two girls given at least one is a girl. Okay, so this now becomes the pool that we're drawing from. So we need to identify how many sample points have at least one girl. Okay, well, it would be this one, and this one. So there are 3. Now, out of those 3, how many of those have two girls in them? Well, just this one right here. So it's 1 out of 3, or 33%. Now in letter C, it says find the probability of having two girls given the older child is a girl. So we're looking for the probability of two girls given the older child is a girl. So now let's narrow it down with our given. So the older child is a girl. Okay, that only happens in this case here and this case here with girl boy and girl girl, which means we have two choices. And then out of those, how many have both girls? Well, only the one. So there's a 1 in 2 chance of having two girls given that the older child is a girl. Here we get 50%. Okay, so hopefully you can see how that given information affects the total number that we're drawing from. All right, you're also going to see some examples with a chart kind of like this. And so these are Proposition X43 results. And we're given two pieces of information. First, the residents, whether they live in the city or live outside the city. And then we're also given whether they're in favor or in opposition. So if we look at this 80 right here, it's saying that 80 people live in the city and are in favor. This 50 people are the 50 people that live in the city but oppose. Okay, these 60 here are in favor and live outside the city, and then these 10 are in opposition and live outside the city. What we want to do is add these to find the totals. So we're going to add across the row. So if we take these 80 and these 50, then we have a total of 130 people who live in the city. If we add 60 and 10, then we get 70 people who live outside the city. If we want to find how many people are in favor of the proposition, we do 80 plus 60, and we get 140. If we want to find how many people are opposed, we would do 50 plus 10 and get 60. Now, if we add along the column here or the row here for the totals, we get 200 either way. And so that's telling me that there were 200 people that were surveyed for this proposition X43. All right, so the first one, if one person is selected at random, find the probability that the person favors proposition X43. So we're looking for the probability that a person favors. Now looking at this, are there any givens? Well, no, we're just looking for favors. So what we're going to look for is the number of people who favor over the total number. Okay, so in this case, in favor is right here, and there are 140 people out of the total, which is 200. Okay, and this would reduce to 7 over 10, or 70%. In our next example, if one person is selected at random, find the probability that the person favors proposition X43 if the person lives in the city. So now we're looking for the probability of favors given that they live in the city. Okay, so what this does right here is narrow down our focus. And what we can do is basically just look at only the people that live in the city. Okay, because we know that for this example, the person has to live in the city. So when we look at this, we know there's 130 people that live in the city, and out of those 130 people that live in the city, 80 of them are in favor. So here we're going to get 80 out of 130, which is 8 in 13. Okay, so we just take what we're looking for out of what we know, and we get 8 out of 13. In the third example, if one person is selected at random, find the probability that the person opposes Prop X43 if the person lives outside the city. So we're looking for the probability of opposing given that they're outside the city. Okay, so this is our condition right here, that they live outside the city. So this is our only concern, and it narrows down our choices. So now we have 70 people that are outside, and then of those outsiders, how many oppose? Well, these are our outsiders, and 10 of them oppose. So we have 10 out of 70, or 1 in 7. All right, so that is using conditional probability to solve probability problems involving dependent events.